All right, so yesterday we ended on this example where we determined the breakaway and break-in points. So basically the breakaway points are points where your root locus on the real axis leaves and becomes complex conjugate poles and then enters. That's the breakaway point. And then the break-in point is when it enters back onto the real axis. The break-in point and breakaway points are found using the transition method and or the magnitude criterion. There's two different ways. Both will yield the um, same break-in and breakaway points. Uh, you might find more solutions when you solve for the roots here, but you only want to consider the points between the poles and between the zeros. One other thing about the breakaway and break-in points is that it's just basically the point where your closed loop poles will once they hit the break-in or breakaway points, the poles become real and repeated before they either become complex conjugates or they become unique real poles. So they always enter at the same spot. And we're skipping this, refining we're the imaginary axis crossing because we didn't cover Routh-Hurwitz criterion. So I actually think this is going to put us slightly ahead of schedule because this also takes a while. But I guess like the takeaway of this point, and I'm not going to test you on this and ask you to find the imaginary axis crossing, but to reiterate the point, if we have a root locus and let's do a different plot. Maybe we'll have maybe something like that. Yeah, let's do a pair of complex conjugates. So first of all, these are our open loop poles and zeros. And then it's going to look something like this. Root locus starts at our open loop poles, ends at our open loop zeros, and it has a break-in point which we can solve for sigma A. And this point here is called our imaginary axis crossing. And one thing we note is that if we pick a point here, this is like K is roughly equal to 0. If we pick a point here, K is approaching infinity. So as we increase K, this is K going up. We're increasing K, and this is symmetric. So it's happening both it's happening symmetrically about the real axis. As we increase K, we're moving our closed loop poles along this trajectory. And when we get to the point where K gets high enough, where it crosses this imaginary axis crossing, and our closed loop poles go from having positive real parts to having negative real parts. And that's the point we're looking for to stabilize a system. So that's where root locus is helpful. We can determine that value of K or the range of K where the system is going to be stable. So that's like the takeaway of of the imaginary axis crossing. We don't really care too much about poles becoming, I mean, we do also care if poles become real and then becomes complex conjugates, but this is, I would say, more crucial because this relates directly to stability. In MATLAB, we can just determine that imaginary crossing K or the imaginary axis crossing by finding the value of K at that point where it doesn't have any real components. But in this class, I wouldn't worry too much about it. All right. So The first part of refining the sketch was break-in and breakaway points. Second part we're skipping. Third part is the angle of departure and arrival from open loop complex poles and zeros. So I kind of talked about that earlier, or I kind of mentioned it in passing. But the angle of departure is basically the angle at which this root locus leaves this complex pole here. So we want to be able to find the angle of departure for open loop poles because we leave from the poles. And then if it's an open loop zero, that's complex conjugate, then it's going to be called the angle of arrival. The method of finding it is the same either way, if it's open loop poles or if it's open loop zeros. And I believe your homework is going to be on finding the angle of departure or arrival. I don't remember off the top of my head. So let's start with this example here. Okay. So I may draw two graphs here on the left. And basically I may draw like an overall like big plot pole zero map where we have oh, and let me give you the poles here. So we have a zero at -2, and we have a pole at -3. And then this here, 2s plus 2, is going to be a pair of complex conjugate poles at -1 plus or minus j. So then we actually have two poles at infinity, or two zeros at infinity, because we have equal number of poles and zeros. Okay, so let's draw the pole zero map at j minus j at -1. Here's 2 minus 2, and then we have -3. So I'm going to draw in red our poles. And then we have a 0 at -2. And right now we can just do the real axis segment and just check that we actually have a real axis segment right there. So we have, yeah, the root locus exists between -3 and -2 because there's an odd number of open loop poles and zeros to the right of this point. So there's only one open loop zero, so that's an odd number, meaning that we meet the angle criteria of 180 degrees times a odd number. Right. So now basically what we're trying to find is we're trying to find the angle of departure here. So in my second plot here, I'm just going to draw like a close up of the pole in the top left, like in the top right there at j at 1 -1, I mean, at j. So we look at this pole here. We're trying to find the angle at which it leaves, and I'm going to define this point here with a length of, I'm going to say epsilon. It's very close. They're basically the same points. And so then what we're trying to find is this angle here. And I mean, so I'm going to call this theta 1. We're trying to find theta 1. All right. So epsilon's basically at the pole. So what we're going to do is we're going to pick a point. So basically what we're doing is we're picking a point close to -1 plus j. We can also pick this one as well. We can pick a point close to -1 minus j. It doesn't matter because this is symmetric about the real axis. So whatever angle we get for like this for theta 1, the bottom angle is going to be negative theta 1 because they're symmetric. So we pick a point close to -1 plus j, and basically we're saying epsilon is basically at -1 plus j. They're the same point. So then we evaluate. Since there's the same point, we know the root locus exists on the open loop hole. So we evaluate the angle at -1 plus j. And we solve, and then using that, we solve for theta 1. So that's what we're doing. So if I were to draw the angles here, basically this is going to have an angle of theta 1. So we're solving for theta 1. I'm going to call this the angle of this theta 2. And let me just draw a little horizontal line there to indicate that that's our reference point. I'm going to call this V1, and then I'm going to call this theta 3. So we're going to find the angles. And we know that the point we are evaluating exists on the root locus because the open loop pole is the starting point of the root locus. So then let's apply the magnitude, or not the angle criterion. And we get 2i plus 1 multiplied by 180 degrees is equal to sum of the angles of the zeros minus sum of the angle of the poles, which is equal to B1 minus theta 1 plus theta 2 plus theta 3. Any questions so far? Okay, so we're solving for theta 1. So we don't know what theta 1 is, but we know we can find phi 1, theta 2, and theta 3. Let's start with theta 2 first. I mean, I don't even need to plug in my calculator. This point is directly vertical to theta 1. It's just 90 degrees because this is a 90-degree angle. But if you want to see the math for it, it's going to be our evaluated point, which has a height of 1, minus our pole location, which is -1, divided by our evaluated point, which is at -1, minus our pole, which is at -1, which is equal to arctan of 2 over 0. And when we take the arctan of infinity, or a very, very big number, this value approaches 90 degrees. let's say we're solving, if we were out evaluating at theta 2, let's say we're actually finding theta 1 and we were trying to pick a point at -1 minus j. If we were evaluating that point, uh, then we would be finding theta, we would be solving for theta 2. Then theta 1 would not be 90 degrees. It would either be 270 degrees or minus 90 degrees. Because we're referencing down, like our reference point is the positive x-axis, but then the evaluated point is down in the negative y direction. So we had to go to 270 degrees or minus 90 degrees. So this is why I like to draw it out. It's really easy to see how our angles are referenced. Okay, so theta 3, we're going to solve for that. It's going to be arctan of our reference point, the height, minus the pole location, the height of the pole location, which is 0. And then it's going to be the length, which is -1, minus the pole location, which is -3. We get arctan of 1/3, and that's going to be 26.6 degrees. Oh yeah, it's 2. Thank you. And then for phi, I can tell it's 41 degree or 45 degrees because it's height of 1/1. But just to be complete, I'm just going to write everything out. It's going to be 1 minus 0 divided by 1 minus -2, which is equal to arctan of 1/1, which is equal to 45 degrees. All right, so now that we got that, we just solve for, we plug it back in, we get 2i plus 1 multiplied by 180 degrees is equal to, let's see, 45 minus theta 1 minus 90 degrees minus 26.6 degrees. Another way of thinking about it is that theta 1 is equal to I guess to be thorough, 2i plus 1 multiplied by 180 degrees minus 71.6 degrees. So now at this point, we can just start plugging in values of I until, yeah. So we say that I is equal to 0, we get negative 251.6 degrees for n is equal to 0. So this doesn't seem like a number that makes sense. If you add 360 degrees, because that doesn't change it, we actually get 108.4 degrees. And now we can say that, all right, our angle of departures for this is going to look like this. Where this initial angle here is 108.4 degrees. So then this angle here is minus 108.4 degrees. if I actually want to make this sketch even more refined, I actually know that this root locus at infinity is going to converge to a vertical line. So I can find my asymptote. So it can converge to this asymptote here. And we can determine this value if we want to make it really defined. Sigma A is going to converge to this point here. The reason why I know that is because if we look at our angle, maybe I'll just write it out on the side here. Little side note. I'll do it in green because I have the asymptotes. Little side note. Our asymptote angle is going to be equal to 180 times, it's going to be 2i plus 1 times 180 degrees divided by number of finite poles minus number of finite zeros. And we have 3 finite poles and 1 0. So then we just get 2i plus 1 multiplied by 90 degrees. And if we vary I, we get 2 unique angles, which is 90 degrees and 270 degrees. So that means we have an asymptote going up, asymptote going down. So I know that this angle of departure, which is super shallow at 108 degrees, it's like barely obtuse, is going to converge to 90 degrees. Or it's going to converge to like this asymptote here. And then we can find the asymptote location if we want, but I'm not going to. Any questions? So this is kind of what I want you to think about whenever you're drawing root locus. When you draw these branches that are going to infinity, think about if they're going to infinity at a vertical line or are they going to infinity at angle. Think about the asymptotes, asymptote locations, and then break in and breakaway points. Any questions? Good. All right, so then chapter 8.8 talks about the generalized root locus. And basically, we define the root locus by varying k, but what if we have a desired k and have another unknown parameter, like let's say an unknown pole? So here in this example, um, k is equal to 10. And then when we put this into our closed loop transfer function, actually, I should be careful. I would ignore the k is equal to 10 because k is here, g has 10, but it's just going to be kg of s divided by 1 plus kg of s h of s. And then we get 10 over s plus 2, s plus p1 divided by 1 plus 10 over s plus 2 times s plus p1. And then for our overall closed loop transfer function, we get 10 over s squared plus 2s plus 10 plus p1 times s plus 2. All right. So what we're trying to do is we're isolating this unknown here. So then we're going to divide, seems a little backwards, but we're going to divide everything by s squared plus 2s plus 10, which is this term here. And we get this. T of s is equal to 10 over s squared plus 2s plus 10 divided by 1 plus p1 s plus 2 divided by s squared plus 2s plus 10. And basically what we're trying to say is now we can redefine this as k g of s divided by 1 plus k g of s h of s. So now instead of we basically moved this term here and we put it into h. So now we get instead a new definition of k g of s h of s is equal to p1 s plus 2 divided by s squared plus 2s plus 10. So now what we can do here is we can draw the root locus because basically this p here is now the k term. And we can draw the root locus as a function of p1, which is our open loop pole in our original system. It's just a little trick. I'm not exactly sure what the purpose of this trick is. I haven't really found an application for it, but the book mentions it, and I thought it was just worth. It's like a different approach to root locus, but same exact concept, just applied slightly differently. So this is going to conclude chapter 8 on root locus. I'm going to upload the notes today, and then we'll start chapter 9. Just some takeaway. Root locus is a visual tool that gives us a qualitative description of the closed loop pole locations. The number of branches is equal to the number of closed loop poles, and all branches start at the open loop poles and end at the open loop zeros. There are equal number of poles and zeros when including finite and infinite poles and zeros. And the root locus can be used to help select the system gain, K, and closed loop pole locations for desired transient response. That ends that. I just have a very, very brief demo on how to use root locus. I just have a generic transfer function here, G, and with some tricks here. Yep, tricks. I'll explain you what's going on. So here we use the command R locus, and you can see the root locus here. Everything's just stays on the real axis. And if I pick a point here, so we have 3 closed loop poles, and if I pick this point here, you can see the gain increase in the pole location. So let's say if I want to pick a system with a gain of 8.75, let me remove that point if I can. I'll click that again. Then my second pole is going to be around here at also 8.75. Close enough. And then my third pole is also going to be here at 8.75. Something like that. So I have a pull out 4.25, a pull out 2, and a pull out minus 14. Notice that as we increase the gain K, it moves towards our open loop 0, and it goes from like 100 to infinity, just like that. So one trick I like to use is Pauli. So let's say I gave you the poles and zeros of the system, and I say, okay, we have a 0 at -1, a 0 at -2, or -3, and a 0 at 4, or something like that. Then when I click enter, this finds the coefficients of my polynomial equation. So my polynomial equation here is going to be s to the fourth, or s cubed, plus 0s squared, plus minus 13s minus 12. So a really handy feature. I have 4 roots, then it's going to be s to the fifth minus 3s to the fourth minus 13s. Oh, sorry. S to the fourth minus 3s cubed minus 13s squared plus 27s plus 36. Yeah, it's exactly. It's the opposite of the roots function. So in the roots function, if I have a coefficient that's like s squared plus 2s plus 2, it gives you the roots. Yeah, so it does opposite of the roots. Yeah. Notice here that the pole of G has a positive pole at 4, and then if you type in 0 of G, it gives you the zeros of G. And then if we do PZ map of G, we can also see the pole 0 map of G. Although, what I like about root locus is that we are going to what I like about root locus is that it just draws the pole 0 map of G and then shows you all the possible closed loop pole locations. And here we can look at this root locus, and we can tell that this system can never be stabilized because of this closed loop pole staying only in the right half plane. So there's no point trying to stabilize the system. You have to add a controller here. So if I remove that pole at +4, the system's going to become stable. Or it might be stabilizable. So now the system is stabilizable because our closed loop poles start in the right half plane, but they cross the imaginary axis crossing right here at gain of 0.3 roughly, and then it becomes stable. And let's say I want to build a system. I want to stabilize the system. I'll choose gain of 1.15 and a gain of, so gain of 0.15. So basically my closed loop poles will be right here. Oh, you know what? I don't think I'm sharing my screen. Oh, damn. Yeah. Screen got disconnected. Yeah. Oh my God. Well, there you go. Sorry, online folks. All right. So just really brief recap. Uh, Here I'm just defining my transfer function using poly. Poly just lets me put in the roots of a polynomial equation and it gives me the coefficients. Use that to define transfer function, and I use R locus to find the root locus right here. So then I have this root locus here, and you can see that the system is stabilizable because the closed loop poles are in the domain of the left half plane. And here I'm going to just choose a gain of 0.15 for my closed loop transfer function. So I'm choosing 0.15. Poles is at minus 0.7 plus 1.76. So what I'm going to do here is I say like, okay, like I like system is stable at k is equal to 0.15. Then what I'm going to do is I'm going to create my closed loop system. I'm going to choose 0.15 as my gain, multiply that by k, and we're going to have a negative feedback system. And then we're going to just check the pole of t to make sure that matches what the root locus is at. So negative 0.78 plus 1.16 or 76, which is correct. So T is stable. That's how we use root locus. We find the gain and then we put it in this closed loop transfer function and we apply the gain here. One thing to know about root locus is if I increase, let's say, if I increase the gain of my open loop transfer function by 2, then I'm going to have to divide this by 2 here to get the same system, I believe. Nope. No. Let's look. So if I increase the gain by 2, then let's go back to that point there. Negative 0.78, I believe, was the pole location. It is 0.076. It is actually 0.15 divided by 2. So let's try that again. Yeah, well, I'll look into that later. Anyway, that's how you use root locus on MATLAB. You can see your head. All right, so then now we're going to start chapter 9. And this is broken up into 2 parts. So this is designed via root locus part 1 because this lecture slide is so long. So there's gonna be a part 2 to this. So this is a long lecture. It's one of 2 parts, but it's an important section. Chapter 9 covers design of PID controllers, the most common controller used in 90% of controls industry, and the methodology covered in Chapter 9 for PID controller design uses root locus technique, which is not very common. You don't use root locus to design PID controllers. You just tune PID controllers by just playing around with it and just seeing how your output responds. But it's important to know what but root locus is a good visual to show you what each component does. Oh yeah, so however, root locus shows the effect of each component graphically. In reality, PID tuning, like adjusting gain and looking at the output, is used as the design. For example, you have the Ziegler-Nichols method, the Tarius-Liobin, and the flexibility of PID controller allows us to apply on unknown systems. So we can apply this on systems where we don't know the model. And PID controllers, what they use as the input to the controller is error. So it uses error. So as long as we have an output and we have our desired input, we can use a PID controller on it. So we're going to talk about we're going to have an introduction, and then we're going to start with PD compensators, and then the equivalent version called lead compensators. And then in part 2, we're going to talk about PI compensators, or PI controllers and lag compensators. And then we're combine it into a PID and lead and lag compensator. So just a little introduction to chapter 9. So the root locus shows us the viable closed loop pole locations, but there are regions on the complex plane that we cannot reach. I need to fix this plane. On the complex plane, we cannot reach. We are limited to those responses that exist along the root locus. So let's say, so in the textbook, they have this little graph here where this blue here is our root locus, and point B is actually what we want, but point A is the closest point we can get to it. So they call this our desired location. And this is our best we can get. One other thing to note about this pole 0 map, this line here is where damping ratio is constant. Just a nice little property. So we can get A to have the same damping ratio as B, but we won't have the same natural frequency or the same decay component. So one thing I can tell you for sure, just from looking at this pole zero map, is that B has a faster transient response. It has a faster transient response than A because we have a more negative pole. Because since B has a more negative pole, it's the K ray is going to be faster. However, we do know that the percent overshoot of B is equal to the percent overshoot of A. And that's because percent overshoot is only dependent on your damping ratio. One little thing I want to note about the relationship of damping ratio being constant, there's actually another component to this as well. You can actually have a constant natural frequency as well. I'll show you what that looks like. So we have our imaginary axis, our real axis, and let's say we have a pole here. So we know that this length here, or maybe you don't know, but I have told you that the length here is the natural frequency. This is our natural frequency, the negative natural frequency multiplied by the damping ratio. And this height here is J times omega D, which is the damped frequency, which is equal to J times omega n times square root of 1 minus zeta squared. So in red here, I'm going to say like damping ratio is constant, zeta is constant. And maybe here, this line here is when zeta is equal to 1. And the reason why it's zeta is equal to 1 is because there's no imaginary component. So this 1 minus 1 becomes 0. So then we only have a pure pure decay here. So as we go down here, zeta increases. But we draw these like these straight lines, that's the constant line for damping ratio. Now the other relationship that's useful is if I draw a circle, let me try to encompass this. This is where our natural frequency is constant. Because you see there, our natural frequency is just the radius of the circle is our natural frequency. So as the circle gets bigger, our natural frequency increases. That's the relationship when you look at these poles. So if I were to give you a design objective where I want my natural frequency to be some value and my damping ratio to be some other value, you can basically find the intersection point of the red and purple line, and that's going to be our desired closed loop pole. Or you can just plug it into this negative omega natural, like we can plug it into this value and this value here to get that point as well. Either way works. Oh, crap. Screen disappeared. I guess that's a sign we can just call it for today. We can talk about the limitations tomorrow. All right. Thank you.